Let's go into some details about how MOSFETs and CMOS devices work. And so this is going to be a review if you've taken a logic design class or if you've taken an integrated circuits class. So before we do that, just a quick survey. How much of this stuff do you guys know? So which one of these topics would you feel comfortable explaining to a colleague? So there's no right answer here, this is just a survey. We're going to go through all of these things in a little bit of detail, but I just wanted to get a feeling for what your background here is. All right, so how does a MOSFET work? And to start out, what is a MOSFET? Well, a MOSFET is a metal oxide semiconductor field effect transistor. So it's a field effect transistor that's built with metals and oxides. That's how you form the gate and the resistor under, resistor under the gate, and then the semiconductor. So let's take a look at it. We have a bulk silicon here, and we're going to build ourselves a MOSFET. So we're going to put in one area of doped material. This is going to be our source, and it's doped so that it will conduct. The bulk here is a semiconductor, so it isn't going to conduct electricity by default. We need to dope the source here with either P or N type ions to make it conduct. We've got a source and a drain. And now the idea of a transistor is that somehow we're going to take this bulk in the middle and we're going to magically transform it from an insulator, which is what it is now, into a conductor so that we can pass electricity through it. And this area in between is called the channel. And on top of the channel we're going to put a gate, and the gate is going to be the connector that we're going to use to transform this from an insulator into a conductor. Now if we put the gate right here, then electricity would just flow straight into the gate. So instead what we do is we put an insulator, an oxide between here. And this insulator here prevents electricity from flowing between the gate and the channel itself. All right. So the way this works is we put charge on the gate. So if we put charge on the gate here, it's going to build up a voltage. Because if you look at this gate to the channel, here we've got an insulator. This is a plate capacitor. So here are the two plates. So if we put charge on the top here, we're going to build up a voltage for it. Sorry, over on this side. Here we are. We put the charge on here, and now this charge is going to build up a capacitance. Sorry, this charge up here makes a voltage across here. All right. So what happens? Well, if we've got a bunch of positive charges over here, we're going to have something come under it. So a bunch of electrons are going to come out of the bulk here in order to form an inversion layer in the channel. That is, the positive charge up here across this capacitor is going to pull negative charge in here. Positive charge always pulls negative charge. And so now what we've done is we've changed this channel. It used to be sort of a non-conducting channel, but now by putting this voltage up here, we've pulled charges into it. It's called an inversion layer, and we've made the channel conductive. Okay, this is great. So we've made the channel conductive. Now we can get power to go through here. So now the channel is a conductor, and we can have charge flow through here. So if we put a differential voltage across our source and our drain, we're going to get electrons flowing through it. So this is the way a transistor works. We've got this sort of capacitor here between the gate. We put charge on the gate. It pulls charges into the channel, changes the channel from an insulator to a conductor, and then if we put a voltage across the source and the drain, we can get electricity to flow through it. All right, so let's ask a question about this. Is there a difference between the source and the drain? Well, the answer is no, there is no difference. The devices are completely symmetric in how they're built. What is the source and the drain is just which supplies the electrons and which accepts them. So if we have it set up this way, we have electrons coming from the source going to the drain. If we switched V plus and V minus, well, we just switch the tables and it would go the other way. But the structure is exactly the same. The source and drain are just the directions that the electricity flows. There's another question. How many terminals does the MOSFET have? So you can see what I've drawn here. Is there something missing? Well, there is something missing. So a MOSFET has 4 terminals. Here we see 3 of them. We've got the source, the drain, and the gate. But we've got to hook up the bulk here. So we need another part over here. So we need another terminal that plugs into the bulk. And the way to think about this is these electrons here, they have to come from somewhere. And they're going to come through the bulk. So the bulk has to be hooked up to the supply or the ground. And in fact, if the bulk here was hooked up to a positive supply, well, then we'd already have positive electrons in here, and putting positive ones in here wouldn't help us as much because this would be overly charged. Sorry, not overly charged. It would have the wrong carriers in it. So we need to have this connection here to the bulk in order to supply the carriers that are going to show up in the channel and to make sure it's biased correctly so that this capacitor works the way we expect when we put a charge on here. All right, what determines the speed of a MOSFET? Well, it's obviously how fast the electrons can flow through here. So if we have a really fast transistor, it means that these electrons can flow quickly from the source drain through the channel. Well, what limits that? So what can we do to make this MOSFET faster? Well, to make the MOSFET faster, we want to increase the voltages. So if we increase the voltage difference between the source and the drain, that means there's a stronger field pulling electrons through here, so the electrons will move faster, which means there's a higher current. If we increase the voltage on the gate here, it means it's going to pull more of these carriers into the channel, which makes the channel conduct more. So the higher voltage we have on a gate, and the higher the difference in voltage we have between the source and the drain, the faster the transistor will work. Okay, so there are other parts that affect the speed of the transistor in terms of the design and how it's built. So the thickness of the oxide is one of them. So the thinner you can make the oxide, the closer the charge on the gate is to the channel. That means it can have more of an effect. Remember from your basic physics classes that the effect of a charge falls off as the square root of the distance. So if I can make this oxide thinner, I can have this voltage pull more charge into the channel, which means the channel has more charge and it will have a faster transistor. There are other effects also. So the doping here. So the source and drain are doped material, that is, they have ions implanted in them to make them conduct electricity. Remember, the bulk doesn't conduct by default. The higher a doping you have here, the faster electricity will move through that. Also, the gate material itself makes a big difference. For a long time, the gate material was just a doped oxide, but it didn't move electrons through it very quickly, so now they've switched to using metal gates in order to move the electrons more quickly and make it go faster. So there are two things to take away from this. You can change how you build transistors to make them faster, but in terms of the operation of a transistor, it will be slower if you have a lower voltage. So a lower voltage means I can pull less electrons onto the gate, which gives me less in the channel, and a lower voltage across the source and the drain means I have less force to pull electrons through the channel itself. All right, so how do we get from MOSFETs to CMOS? So CMOS is what we build things with, and this is complementary metal oxide semiconductors. So complementary means we're going to have two different parts here. And the two different parts are nmos, it's an n-doped transistor, and these are a little bit of the faster type. And they have the following characteristics. They turn on with a positive voltage, and they're good at conducting to ground, so sending electrons to the ground. So here's what an nmos device looks like. You can say I've connected to ground because it's going to be good at moving electrons to the ground. Here's the gate and the source and the drain. Now PMOS, these are p-doped type. They're slower, and they're slower because the p carriers, the holes, move more slowly than the electrons. They turn on when you get a low voltage, and they're good at connecting to the positive voltage. So they're good at passing a 1. So here's one of those, and we distinguish them by having a PMOS having this circle here. All right, now in CMOS we have complementary designs. That means we have both NMOS and PMOS, and they're complementary because one is good at signaling zeros and the other is good at signaling ones. You put them together, we can do both ones and zeros, which is, kind of helpful if you want to build things with ones and zeros. So let's take a look at how this works. So here's my circuit. I'm going to hook up an in to it here, and here's my out. Now I'm expecting that most of you know what this circuit already does, but let's walk through how it works. So here's our circuit. Say I have a positive voltage on going into the in here. Now a positive voltage is not going to turn on the PMOS device. Remember, it turns on with the low voltage, but it is going to turn on the NMOS device. So if I turn on the NMOS device, I'm going to have a conductor across the NMOS device. That means I'm going to be able to pull electrons down to ground here. So what that means is I'm going to get out a 0 here, because when I put a positive voltage in here, it's going to turn on this device. This device is going to connect the output to ground, so the output voltage is going to go down to the ground voltage, or 0. What about the other way around? Well, if I put a ground, or a 0 into here, this device is going to turn off, and the PMOS device is going to turn on. And when the PMOS device turns on, I'm going to allow current to flow to V+. So that means our output is now going to be a 1 or a plus. So this is an inverter. And it's complementary because I use both the PMOS and the NMOS. The NMOS device is what pulls my output down to 0, and the PMOS device is what pulls the output up to 1. All right, so here's our CMOS inverter. A few things to note about it. PMOS devices are slower because they have a channel that moves holes, not electrons, so they're PMOS. And what that means is they're generally larger. So if you build this device in your logic, you'll probably make the size of the PMOS one a little bit larger, so you get more holes, so that it'll move the same amount of charge in the same amount of time as the NMOS device, so that the switching from 0 to 1 and 1 to 0 will be about the same. Now here's a fun fact from a historical perspective. A long time ago, we didn't have CMOS, we just had NMOS, so no P devices. So how would you build an inverter if you didn't have this device up here? So here's a start. Here's an NMOS only inverter, and this is not quite going to work. So it'll work if I put in a 1 here. If I put in a 1, this will turn on, it'll pull it down to a 0. But if I put in a 0 here, nothing's going to happen. This output's just going to be disconnected because this channel won't conduct. So what did people do? Well, they just put in a resistor. I just put in a resistor here that always pulled it up to positive voltage. And this burned a lot of power. So if I go and turn on this device, so I put in a 1 here, I want to get a 0 out, now I'm going to be constantly moving electricity all the way through here because the top part's not turned off. If I turn this off, however, then there won't be any electricity flow through, so I'll just get it from up here. If you look at the complementary one, when this gate is on, this one is off, so we don't have electricity flowing all the way through. And vice versa, when this one is on, this one is off, so we don't have electricity flowing all the way through. So back when we were using NMOS, power was much less of a concern, so people really didn't worry about this.